Hello, this is the final presentation for Nightwing AI Transcribe, a portable real-time communication intelligence system developed by Group 24. The team includes 4 members, Elena Thurner and Sophia Demers, both majoring in electrical engineering, and Christine Hawkins and Simeon Feliz, both majoring in computer engineering. The project was developed to address a growing need for secure, real-time communication in environments where cloud systems are too risky or unreliable. By processing audio locally on the Jetson Orin Nano, the system reduces latency, protects privacy, and works completely offline, making it ideal for mobile, field-based use. This project was sponsored by Nightwing, a cybersecurity company focused on outreach and recruiting at UCF. It will also be used in client demos to showcase secure, real-time communication monitoring. Nightwing AI Transcribe is built for these exact scenarios. In high-stakes operations, real-time access to transcriptions and translations of foreign radio chatter can be a game-changer. This fully autonomous system captures, transcribes, and translates intercepted communications instantly and without relying on external networks. Here's a high-level view of our system. It begins with RF signal capture and processing, followed by real-time transcription and translation using Whisper AI. Finally, all data is sent to the ESP32, which handles the user interface and transmits results to a connected Android device.
Here's an overview of our basic system goals. We want to capture radio signals in real time with minimal noise to ensure clean and accurate processing. The system will then transcribe and translate those signals instantly, even across languages. For discrete communication, it'll send the translated text to a mobile device using a wireless method that doesn't rely on Wi-Fi. Finally, everything will be housed in a compact, portable design to keep it mobile and low profile. For our advanced goals, we would be aiming to add AI voice recognition that can tell speakers apart, improving translation accuracy, and for the mobile app to let users customize language settings and manage data. For stretch goals, we would want to support multi-language translation, allow users to tune into different frequencies, and enable two-way signal communication. We're also exploring AI-generated voice emulation based on captured audio. Our main objectives are to capture radio signals with minimal noise, enabling clean, real-time processing. We'll stream that data into an AI module for accurate transcription and translation from foreign languages into English. The system will use a discrete wireless connection, like Bluetooth, for secure communication with a mobile app. That app will display translated speech to text in real time and show system status updates. Finally, the device will be designed to be portable, discreet, and easy to use in various environments. Here we have our engineering specifications. Our 3 key engineering specifications include the latency of the translation and transcribing being less than 5 seconds, for the average of the confidence to be above 60%, and for the Bluetooth connectivity to be greater than 25 feet. This house of quality shows how our sponsors' needs like portability, accuracy, speed, power efficiency, and affordability translate into specific engineering requirements. Our engineering targets are listed at the bottom, guiding the physical and performance limits we designed around.
The system combines an SDR, a single-board computer, sensors, custom PCBs, and a touchscreen, all integrated into a compact portable enclosure.
This is our system's hardware layout. Power starts at the AC-DC power supply, which outputs 5 volts and 110 volts. The 110 volts powers the Jetson Orin Nano, while the 5 volts goes to a buck converter that steps it down to 3.3 volts for the MCU. 2 current sensor PCBs monitor power usage, one for the Jetson and one for the ESP32 system. The Jetson receives raw PCM data from the SDR and sends transcribed messages to the MCU over UART. The MCU handles communication with the LCD touchscreen via SPI and also manages the emergency stop and status LEDs. It sends Bluetooth messages to the mobile app, which displays live translated speech-to-text and system updates.
This chart compares the Jetson Orin Nano, Raspberry Pi 4, and BeagleBone Black. The Jetson stands out for its 6-core CPU, 1024-core GPU, and native AI support, making it ideal for our system in real-time signal processing. Although the Raspberry Pi is versatile for general computing, it really lacks the native AI acceleration. And the BeagleBone Black, while low-powered, it excels in hardware interfacing, but it draws as low as 2 to 5 watts, depending on the workload. This chart compares NVIDIA's Jetson's lineup. The AGX Orin delivers the highest performance, and the Jetson Orin Nano is the best choice for us because it is a balance between power and cost, and it also offers up to 40 TOPS and just 7 to 15 watts. The entry-level Jetson Nano is best for simpler text, but since we're going to do real translation and transcription with the AI model, we decided to choose the Jetson Aura Nano series.
We chose to use a software-defined radio because unlike traditional radios, SDRs can adapt to different signal types through software alone, which makes them ideal for real-time communication analysis in dynamic environments like ours. Here's a comparison of different SDRs, and, as highlighted, we chose the Pluto SDR. It provides a great balance of performance, flexibility, and cost. It's user-friendly, supports transmission, and meets our project's needs without unnecessary complexity or high cost.
We compared MCUs and FPGAs and chose an MCU for its power efficiency, simplicity, and lower cost. The MCU handles power monitoring, communication with the Jetson, and Bluetooth transmission to the Android device. Since the Jetson performs the heavy processing, using an FPGA would have been unnecessary and overly complex. The MCU offers a practical and efficient solution for our system. We compared the ESP32, MSP430, and Arduino Uno and chose the ESP32 for its built-in Bluetooth, strong processing power, and low cost. Its wireless connectivity and high speed make it ideal for UART communication with the Jetson, Bluetooth transmission, and power monitoring, making it the most efficient and cost-effective choice for our system. We compared 4 regulators to step down 5 volts to 3.3 volts and chose the MP2338. The MP2338 offered the best balance with its wide input range, 3A max output, and moderate switching frequency. Its stable regulation and power capacity made it the ideal choice for our system.
These are the different ASR frameworks. VAL stands out for its low resource support and offline functionality, which was one of our top contenders in choosing a framework. The NVIDIA Reval offers multilingual support but is really resource heavy. The Jetson Voice is tailored for Jetson devices but has limited documentation. However, we ended up choosing the Whisper AI by OpenAI model because it provides high accuracy and translation in many languages, making it great for real-time multilingual transcription, which is key for our system. Lastly, the Pico Voice is optimized for keyword spotting and low-power tasks. The Whisper and the VOS were the strongest for the Jetson Aura Nano integration, but we decided to do the Whisper because of its high translation capabilities.
We selected GNU Radio for its open source flexibility, strong real-time performance, and seamless integration with the Pluto SDR. It also supports custom development with Python and C++, making it ideal for a system that needed low latency and full control over signal flow.
For the Nightwing AI Transcribe project, we chose to tailor our handheld OS selection on 3 main factors: programming restrictions, ease of programmability, and public availability. Android OS proved to be a top contender in these comparisons, winning out in each of our consideration criteria with a noticeably large grasp on the public market. One of the most important considerations for our mobile device's hardware after the OS selection was the inclusion of a developer mode, allowing for us to directly access the debugging functionality of the handheld device while developing the application, without the need for external workarounds or nuanced implementation features.
Here we have our overall schematic of our main board, including the linear voltage regulator, USB-A connector, status LED and shutdown button, the USB to UART bridge, and the ESP32. And here we have the overall schematics for the voltage regulator and the current sensor breakout boards. This slide highlights the system's key peripherals and their roles. The touchscreen connects over SPI and lets users start or stop the system and enter the starting battery percentage. Current sensors for both the Jetson and ESP32 use I2C or analog to track power usage. A GPIO connected emergency stop button allows for the manual shutdown, while status LED will show the UART connection to the Jetson. Finally, the USB to UART bridge handles serial communication between the ESP32 and USB port. Here we have the PCB layout for the main ESP32 board, the voltage regulator, and the current sensor boards.
This diagram highlights our communication flow. The SDR sends raw audio to the Jetson over TCP, which processes it and sends JSON over UART to the ESP32. The ESP32 then transmits that data via Bluetooth to the Android app for real-time display.
When the user establishes a Bluetooth connection to the ESP32, the UI software begins to read from the communication channel, searching for serialized JSON data. Upon receiving the transcription information, the UI will begin to parse the information into a text box, adhering to any formatting details selected by the user. So long as this connection is maintained, the ESP32 will continue to send the data over this channel. If the Bluetooth is disconnected, the user will be able to observe the connection status in the app and can take next steps for reconnection. When the user decides they are finished with the transcription, they may opt in to end the transcription, ceasing all JSON printing and enabling the option to save the transcription for later review.
This system use case diagram shows end-to-end flow from capturing a radio signal to delivering transcribed text to the mobile device. Here we see our 6 actors. So the SDR captures and filters the signal. The Genie radio is responsible to start the TCP connection with the Jetson. The Jetson receives the signal, transcribes it, and translates the audio. The JSON formatted result is then sent to the ESP32 via UART, which checks connectivity and forwards it to the mobile device. Users only interact with the mobile device and the LCD screen on the ESP32, keeping the backend process fully automated. Now let's look at the LCD and the ESP32 system flowchart. This flowchart shows how the ESP32 base transcription system starts up, connects via Bluetooth, and begins the real-time transcription. After a 30-second power-up, it waits for Bluetooth pairing. Once connected, it sends a start signal to the Jetson, triggering the transcription script. The system constantly monitors battery levels. If the battery is critically low or the user presses the emergency stop button on the PCB, it disconnects Bluetooth and sends a stop signal to the Jetson, shutting the system down cleanly. This is the Jetson and the ESP32 system flowchart. It shows how they interact with each other. This flowchart outlines the Jetson's background service for handling power modes. After initializing UART, it listens for commands from the ESP32. If it receives a start signal, the system switches to the 15-watt mode, which is high power mode. It initiates the Genie radio and launches the SDR script. If it gets the stop signal, it enters low power mode and shuts down the TCP connection. Then we also have another abort command, which halts everything and stops the SDR, UART, and exits the program entirely. This is the Jetson and the SDR's flowchart of communication. So, as we mentioned, the SDR acts as the TCP server, while the Jetson functions as the client. When Jetson receives a start signal, it enters low power mode and attempts to establish this TCP connection with the SDR. Once connected, it launches the GNU radio flow graph. The GNU radio handles live signal processing, including demodulation and filtering. And while audio data is streamed over TCP for real-time transcription and translation on the Jetson. This is now the UML diagram, which outlines the architecture of the audio processing pipeline, the Whisper model, and the Jetson. So as we can see in the main class, it initializes a subscriber and an audio processor. The subscriber connects to the SDR over TCP and receives audio data. That data flows into the audio processor, which processes these chunks, detects speech, and calculates accuracy. It sends the data to the Whisper model for transcription, and results are transmitted via UART communication using JSON parsing. Meanwhile, Power Manager handles low power mode and restarts the TCP connection when needed.
The Nightwing AI Transcribe's user interface utilizes a global usage of the Bluetooth Manager object that instantiates and handles the wireless connection to the ESP32. Navigation tools are also located throughout the app layout to seamlessly navigate from page to page. In the core functionality of the transcription page, several functions are available in button form, allowing users to format the incoming message, refresh the text box, and even save the transcription data. One of our system's design constraints requires the Bluetooth connection to be present and stable up to 25 feet. Over the course of 3 official test runs, we were able to exceed this distance while maintaining a reliable Bluetooth connection. We also observed that these connection ranges held up in other unofficial tests as well, allowing us to be confident in the viability of the connection at longer distances.
This is our full GNU radio flow graph. It captures the RF signal, filters and demodulates it, then streams raw PCM audio to the Jetson for transcription. We configured the Pluto SDR to receive walkie-talkie transmissions at the specific frequency corresponding to channel 1. The waterfall and frequency sinks confirmed we're receiving a stable signal. We added a low-pass filter to remove high-frequency noise. The output was much cleaner with a sharper signal and a reduced noise floor. To cut out background noise when no one's talking, we used a squelch filter. It blocks low-power signals and only passes audio during transmission. After demodulating the FM signal, we saw a DC offset. We added a DC blocker to center the waveform and improve playback quality. We then resampled the audio to 16 kHz to match Whisper's input. Doing it in GNU Radio lowered latency compared to resampling in the Python script. We also boosted the volume with a small multiply constant.
We did a series of tests to test our latency. We use the same sentence because it eliminates variability from sentence length, complexity, and pronunciation. So in order to calculate our latency calculation, it is from when the transcribed model finishes the transcription and sends it to the phone. That is the length of our latency. Meaning, when the model, as we speak through the walkie-talkie, the model is at the same time transcribing what we speak. So we decided that our latency calculation should be from when the model finishes transcribing to when it is received on the phone. That is why we did multiple tests to test this. We ended up syncing the clock from the Jetson and the ESP32 to see at what time and what latency it took to get the Jetson to the ESP32. We estimated of around 0.02 seconds. This we tested for all 6 tests, which were run 5 times. So this came to an average of 0.02 seconds, which we add as an offset to our latency. So once the Jetson finishes processing and the Whisper model finishes processing the segments and the transcription, that is the time that the latency starts, and we add the offset of 0.02 seconds to add on to calculate the minimal latency it takes from the Jetson's JSON message to get to the ESP32. This slide shows latency performance across 3 key scenarios: Spanish speech, distance testing, and fast-paced speech. In all cases, latency remains under 1.2 seconds, well within the real-time constraints. Even at 50 feet or during rapid speaking, the system processes and transmits audio reliably. This validates the system's robustness under multilingual input, degraded system signals, conditions, and emergency-style communication, ensuring dependable transcription across diverse real-world environments. This slide shows how the model's transcription confidence across different word types, simple and common word phrases like thank you, score above 85% because the model is very confident that what you said was correct, while complex or foreign terms show reduced confidence, and nonsense words, as expected, yield very low scores under 30%. The chart reflects how the Whisper's log probability values correlate with transcription certainty, so the closer to 0 means better confidence that it has. This testing confirms that the system performs well with natural speech and gracefully handles edge cases. So we were able to map it that when it got around negative 0.2 with all the testing we did, it always had a 100% transcription accuracy for us, which means that it had a really high confidence as well. So that is why we mapped it to negative 0.2, because it always got the transcription exactly how it was. Now, if it was lower, like we said, there was more uncertainty within the model, then our expected confidence percentage goes below to a lower value. Now, an average of all the tests we did, our model was still very accurate and still very confident in what it was transcribing, above 60%, because of the parameters we did to fine-tune it.
During testing, we realized the Jetson CPU alone couldn't meet our latency requirements, so we switched to faster Whisper running on the GPU, which gave us a way faster transcription with better efficiency.
Here are the model transcription parameters we use to balance confidence, speed, and efficiency for a low-latency, real-time transcription system. And here are the different Whisper Open AI models that we have tested. We are using small as it gives the smallest latency and highest accuracy. To verify our custom ESP32 PCB, we ran a series of functional tests and compared the results to the ESP32 dev kit. The goal was to ensure it matched the dev kit's capabilities, and through testing, we confirmed that our board performs as expected.
We confirmed the INA 219's accuracy by comparing it to a multimeter and clamp meter, and the readings were consistent.
To test the voltage regulator, I applied different load currents and measured the output. Across 100 to 600 milliamps, the regulator consistently maintained a stable output around 3.3 volts, confirming its reliability under typical operating conditions. To estimate battery life, we calculate the remaining energy by multiplying the battery percentage by 222 watt-hours. Then we divide the system's power consumption about 20 watts to get the runtime in hours. As shown in the table, at 100 we have around 11 hours, and at 10% we have over an hour. The ESP32 uses these thresholds to update the display and automatically shut down the system at 10% to prevent power loss. We originally designed the current sensor for 5-volt measurements, but the Jetson's input is 19 volts. To adapt, we lifted the INA 219's VCC leg and fed 5 volts directly. However, we overlooked the I2C pin still tied to the ESP32. Simultaneously, during manual current testing, we accidentally shorted 19 volts to ground, which resulted in a fried ESP32 confirmed by a short between 3.3 volts and ground, and damaged the Jetson's UART pins, which failed loopback testing. To fix the issue, we designed a new current sensor PCB using the WCS 1800. It works by measuring the magnetic field around the wire, so instead of being in line with the power like the INA 219, it's non-invasive and doesn't interrupt the circuit. It's also electrically isolated from the Jetson, which protects our system from high voltage damage. And as a bonus, we got to mill the board ourselves. To calibrate the current sensor, I ran a known load through a test wire and measured the current with a clamp meter while recording the ADC values. The more measurements I took, the more accurate the results. From the data, I derived a linear equation, just a slope and offset, that converts ADC readings to actual current. The graph here shows the linear relationship I was able to achieve, which is now used in real time for accurate current estimation.
Our total project cost came to approximately $1,667, well under the $3,000 budget provided by Nightwing. Our full work distribution is summarized in this table, reflecting each team member's contributions throughout the project.
This concludes our final presentation for senior design. Thank you.